I'm going to show you another worked example using the bucket and pie theorem. So in this question, you asked to use dimensional analysis to determine the relationship between the torque of this air screw, which is Q, and you've got to develop a relationship in terms of the density, the rotational speed, and the diameter. So using the bucket and pie theorem. So the first part of this is to identify the dependent and independent variables. So our dependent variable is the torque Q, and the independent variables are density, speed, and diameter. Then in the second step, we need to count the number of dependent and independent variables. So in this question we have 4. Okay, so torque, density, speed, and diameter. Then we need to write each variable in its fundamental units. So torque is Newton meters, and if we write newtons as mass times acceleration, and substitute in mass, length, and time, we find that torque is mass times length squared divided by time squared. Density is mass over volume, or mass over length cubed. Now rotation speed, so this is, if we think about it, RPM, revs per second, or revs per minute, so it's 1 over time, okay, and obviously the diameter is just a length scale. Now we need to count the number of fundamental dimensions, J. So we can see that in all of these we have M, L, or T, okay, so J is 3. So before we begin our analysis, we need to select J repeating groups. Now, so we need to select 3 groups, but Q is our dependent variable, so we haven't really got any option here, so we have to choose density, speed, and diameter, and we do see that each of these have mass, length, and time, the three fundamental units as part of them. Okay, so we need to work out our dimensionless groups now. So, and the number that we work out is K, which is the number of variables we have, minus the number of fundamental units that we have. So we have 4 variables, 3 fundamental units, so we only need to find 1 group this time. Okay, so going back to our original statement that the torque is a function of density, rotational speed, and diameter, our first dimensionless group is, which is written in capital Pi, 1 is against our repeating set, which is density, rotational speed, and diameter, but we don't know what this relationship is, so we raise each of these to the power of A, B, and C. We then substitute in the fundamental dimensions. So for Q, we said that it was this relationship. For density it's this, for speed it's this, and for diameter it's this. Now we can work out what A, B, and C are by writing an equation for the exponents for each fundamental unit. So for our dimensionless group, on the left hand side we have no mass, okay, so that's equal to mass, so it's 1 in our first term, A in our second term, and we don't have mass or length in our last 2 terms. If we do it for length, we have it's dimensionless again, so we have no length on this side. We have length squared, so it's 2 for our first term, minus 3A for our second term, no length in this term, and length in our last term. Then we do it again for time, so we have minus 2 for the first term, there's no time in the second term, minus 1 to B, so it's minus B for the third term, and it's not in our last term either. So this is our set of simultaneous equations. So we have 3 equations and 3 unknowns, A, B, and C. So we can solve for that, and if you'll find that A is minus 1, B is minus 2, and C is minus 5. So if we substitute A, B, and C back into our original relationship, we find that for our first pi group is equal to Q over density over rotational speed squared over diameter to the power of 5. Okay, so that's our first dimensionless group. So last step is to relate the dimensionless group the dependent variable with the dimensionless groups and the independent variable. So we substitute back in. But you can see, because we had 4 parameters and 3 fundamental dimensions, we only had one dimensionless group. So we haven't got a function of any other independent variables. So this function, it can't be 0, it's just a constant, k. Okay, so if we times through by the bottom of this dimensionless group, we can see that the torque is equal to some constant times density times rotational speed squared times the diameter to the 5. Okay, so we just now need to do some experiments to determine what k is. And this is actually a special case, I guess, of the Buchanan pi group. And if you do the first few steps and you find out that you only have one dimensionless group, so if you've got 4 variables and 3 fundamental dimensions, or 3 variables and 2 fundamental dimensions, then you're only going to end up with one dimensionless group. So you could kind of skip the last bit and you could just go ahead and write it in this form, that your dependent variable is equal to a constant times some relationship of your other variables. Then if you did it this way and you substituted in the fundamental dimensions, you can just use dimensional homogeneity to work out what A, B and C are. So if we do it for here, notice it's different to, so in all the examples in the Buchanan pi theorem, the left hand side has been 0 because it's been dimensionless, but here it's not. Okay, so here you can see M is 1 on this side and A on this side. Obviously the k is a constant, so it doesn't have any dimensions. So you can write out 3 sets of simultaneous equations, solve for it, and you still get the same answer. So you can see that A is equal to 1, B is equal to 2, and C is equal to 5. Okay, but it's just a quicker way of doing it if you only have one dimensionless group. So how do you find this constant? Well, as I said, we need to do some experiments. So what you normally do is you keep all but one of the variables on the right hand side constant, and then you vary it and you see what the change in torque is with, for example, rotational speed, because the air density is what it is. That's normally constant, and the diameter of the fan is would normally be a good one to take constant. So we just change the speed and look at the torque. So let's say we've done that for a fan which is 0.5 meters in diameter and the air density is 1.2 kilograms per meter cubed. Now if we were to plot a graph of Q against n squared, okay, so remember that's in our relationship, so not against n but again n squared, because it's a n squared in this relationship. And so that gives us a straight line which has a gradient of 2.4 times 10 to the minus 4. Then what is the value of k? Well, if this forms a linear relationship, which we expect it would do based on what we have here, then the general equation for a graph with a straight line is y is equal to the gradient mx plus a constant. So we can write this as q is equal to m n squared plus c. Now at the origin, and we'd expect it to go through the 0, so we expect that if there's no rotational speed, there's no torque, so I c is 0. So we expect the gradient of this m to be equal to k density times d5 for this relationship to be true. So if we know what the value of, so we want to find k, then we know what the gradient of the line is. We were given that in our in the question, and we divide that through by the density and the diameter of the fan, which again we know, and so that gives us the constant for this fan, which is 0.0064. So now we have the relationship for torque based on the independent variables that describe this process.